Okay, I'm going to start now. Yeah, I'm going to start now. Okay, so in case you haven't noticed, this is the first week I've ever lectured. So I definitely want some feedback on how things are going and what I can change for next week and so on and so and things like that, and what we can do to change to make this class good for all of us. So I'm going to stop lecturing a bit early, and then we'll talk about that at the end of the lecture. So you have to maybe think of any comments you have, or questions, or ideas, or whatever. Okay. But for now, let's pick up where we left off yesterday. We were looking at systems. Oh, tell me if my writing's not good enough. We were looking at systems of. We're looking at systems of linear equations. Okay, and we found that you could reduce a system of linear equations, a homogeneous system of linear equations, one which had zeros, all the equations equal 0. You could reduce that really to just a single equation, ax equals 0, where where this A is a matrix or a linear transformation, same thing, and this x is vector and this 0 is a 0 vector. So that A then is a linear transformation from Rn to Rm. And another way of saying that is it's an m by n matrix. So this then is a way of rewriting the system of linear equations. It's called a homogeneous system of linear equations with zeros at the right, and it's another way of writing this thing. I'll write it all out. So the same unknowns in each line. Zeros on the right-hand side, all zeros. And then, because it's going into Rm, must represents m linear equations, because the matrix has got m rows. Okay, so this homogeneous system of linear equations can be represented like that matrix. And then we looked at the question. Well, we found that the question. What solutions does it have, or how many solutions does it have? What are the solutions like? Were really questions about this. Questions about the set of solutions. There are questions about this set, about the set of all solutions, i.e. all vectors in Rn that solve that matrix equation. All vectors in Rn such that Ax equals 0 vector. Okay. So at the very end of the last lecture, we saw that this set of solutions to that equation, or to that system of equations, or to that matrix equation, we saw that set was closed under vector addition. We saw that if you have two solutions and add them together, then the result is still a solution. And to write that down, we saw that if you have x and y in S, then x plus y is in S. In other words, if X was a solution, and Y was a solution, then X plus Y was a solution. And that just occurs because the A is a linear transformation or a matrix, and a linear transformation preserves vector addition. So if you take this, if you calculate what that is, you can write it like that. You can take out the addition, and then since AX is a solution, since AX equals 0, that's 0, and AY equals 0, so that's 0, so the whole thing does equal 0. Okay. Is this, so far, is this okay? Is there any questions about this stuff? Yeah. Oh yeah, okay. That's a good question. So this we want to represent this system of linear equations, right? And so first of all, we note that it's got 1 to n unknowns, right? And in each line they're the same unknowns. Okay. Sorry. The same n unknowns, and then then there's m equations, right? So there's m rows, like 1, 2, let's say m. So this whole equation, this whole system of equations, let me think. I just want to make some more space here. Okay, this system of equations, right? First of all, I can write it. Each equation is a linear combination, but each linear combination uses the same scalars, where the scalars are the unknowns. It uses the same x1, 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 x2, x2, x2. So I can make those the scalars of a linear combination: x1, x2, xn. Okay, and the right-hand side is all these zeros. So I can make that a vector, zeros. Now, how many zeros are there? Sorry? Yeah, exactly, there's m. Okay, so this already tells us that, well, this tells us that the linear transformation that we're trying to represent this system of equations as is going to take things into Rm, because the result on this right-hand side is a vector in Rm, right? Okay, so that tells us that we're going to go into Rm. Okay, and then in front of these linear combinations, in front of these scalars, I put the columns. This column, then this column as vectors. So A11, A21, all the way to AM1, A12, A22, all the way to AM2, A1n, A2n, all the way to AMn. Okay. And this whole thing, right? This whole linear combination, this can be written more succinctly as a matrix, because what matrix multiplication means is this matrix multiplication, x1 to xn, with this being the first column, the first column vector, and the second column vector, and then the nth column vector. By the definition of matrix multiplication, this matrix multiplication is an instruction to give me a linear combination of these columns, with these being the scalars. So this whole thing is just this whole thing. And what are the dimensions of that matrix? Yeah, so that's how you know it's n by n. if you can't, I mean, if you want to, you can go more quickly by looking by. If you figure out that a transformation from n to m, then it's always the second power by the first power. So it's rows by columns. Okay. Oops. Okay. Any other questions about this? You want an example? Okay. So let me do an example. Let me do an example from the tutorial. Okay. So in the tutorial you have this system of linear equations. Okay, and that's a homogeneous system because the right-hand side is just zeros. Now we want to represent this as a matrix equation. So what will be the matrix? Can anyone say? If you times this, so if you look at what the top row of this matrix equation says, it says 1 times x. It says 1 times x plus 2 times y equals 0, and then the next row says 2 times x plus 4 times y equals 0. So these two things are the same. Okay. So that's an example of the correspondence between that linear system and the matrix equation. And then now, in the TUT also, you're asked to prove that the sum of solutions to this system is also a solution, which is an example then of this thing that we showed generally. That the sum of solutions to a system of linear equations is always a solution. So if you have, for example, you have the solution, well, someone give me a solution to this system of equations. 0, 0, yeah? Can you give me a more interesting solution, please? 2 minus 1, yeah. And another one? Yep, okay. And these are all elements of this set S, the set of all xy, the set of all vectors in R2, such that a xy equals the 0 vector, where a is this. Right? Okay, and now if you add any of these two solutions, you'll get another solution. For example, you take 2 minus 1 and add it to 4 minus 2, you'll get 6 minus 3, which is also in S, which is also a solution to this system. It's also a solution to that matrix equation. So this is a concrete example. This is a concrete example of this general thing that the sum of solutions to a system of linear equations is also a solution. So in other words, let me just change color. Okay, so in other words, this set S is closed under vector addition. Okay, so I think, yeah, at the end of last lecture I asked, can anyone say what other structure it has? What else is this closed in under? Has anyone thought of that, or does anyone know? Yeah, right, it's closed under scalar multiplication. So S is also closed under scalar multiplication. Okay, and now we should try and prove that. Okay, So let's take any scalar alpha, and let's take any solution. So that's anything in the set S. So in that set, the set of solutions. Now you want to try and show that alpha x is also in S. So how do we do that? We check to see if it solves the equation. So we see if you go A alpha x, what do you get? What should the next step be? It will become 0, but how do I know that? Since it's linear, yeah. Since A is a linear transformation, or it's a matrix, same thing, you can take this alpha out, and this becomes A times alpha x, and then, alpha times AX, and then the AX is 0 because x is in this set S. So AX equals 0. So we have A 0, and so alpha times 0 is 0. So that proves then that alpha x is in S. So this set then S, the set of solutions to AX equals 0 is also closed on scalar multiplication. So then what is the set S? What is its structure? If it's closed under vector addition and it's closed under scalar multiplication. Yeah, so it's a vector space. That's okay. We've proven that S, the set of solutions, is a vector space. Okay? Which vector space? How many dimensions does it have? I think did someone say 2? Okay, R2. So maybe S is R2. Maybe S is R2. Okay. Well, someone give me a random vector in R2. 2, 1, right? Is 2, 1 in S? Is 2, 1 in S? Oh, I'm sorry. Now we're thinking of the actual example, the particular example of this matrix, right? Okay. So in this case, then she's suggesting that S equals R2. Okay. Sorry. Now is 2, 1 in this set S? Does 2, 1 solve that equation? It doesn't, right? So that means that can everyone see why 2, 1? Why if you put 2, 1 in, you put 2, 1 in there, the equation doesn't work out, right? You don't get 0. Okay. So 2, 1 is not in S. Okay. So that means that S cannot be R2. It cannot be everything in R2. Yeah.
So then is it a straight line minus half x?
Yeah, it is. It is. Okay, so in this case, you have S is actually equal to, so it's S can be, you can see maybe that S can be any multiple of 2 minus 1, right? So S equals the set of all things or multiples of 2 minus 1. And that is a straight line going to the origin with negative slope. Okay. This line x equals minus 2y, right? Okay. So S is not equal to R2 in this case, but S is a subset of R2, right? Everything in S is in R2. It's not the whole of R2, but it's some of R2. So we can say that S is contained in R2. S is subsets of R2. And we proved that S was a vector space. We proved that for the general case of Rn. So it does hold in this R2 case. So, and when you have the situation, when you have a subset of a vector space, and that subset is itself a vector space, which doesn't always have to be. You can have subsets of vector spaces that aren't themselves vector spaces, that aren't closed under vector addition and scalar multiplication. But when you have a subset that is a vector space, then that's called a subspace. So a subset S of a vector space is called a subspace when S is itself a vector space, i.e. when S itself is closed under vector addition and scalar multiplication. Okay. Now this thing holds. We're looking at R2. This kind of thing holds generally. If you have the general problem, you have this general problem of trying to find this S. This S will always be a subset of R what?
Rn.
Yeah, Rn, because all these X's are in Rn. It'll be a subset of Rn. It'll actually be a subspace of Rn because it's a vector space, because it's closed under vector addition and scalar multiplication. So the question, what is the structure? What is the structure of the set of solutions? How are different solutions relate to each other? How do you get one solution from another? That's answered by by saying, well, the set of solutions is a vector space. To get new solutions, do whatever you want. Do whatever things you normally do in a vector space. Add vectors together, scalar, multiply, whatever. And in this case, in this particular case of when A was this thing, and it's 2 by 2 case, the particular subspace we get is this line that goes through the origin. Are people following? Any questions about what we've done so far? Oh yeah.
Do you mind if you take a bit more time on the slide so we can actually get to it?
Yeah, sorry, yeah. I can also upload these to Vula afterwards, if that's helpful at all. But yeah, I'll try and go slow. Okay. Yeah?
So I just ask, so you're saying that for a vector space to be a vector space, you can add, subtract, whatever,
Yeah.
but is that limited to just that and multiplying by scalar? You obviously can't square or whatever. So
Yeah, you can't, no,
so
yeah, you can't square.
limited to
Yeah,
that.
just the operations of the vector space, adding and multiplying. That's all, yeah. It's just that you can add two vectors together, and then you can add another vector to that, and then you can add another vector to that. You can add, you can multiply them by any scalar. So you end up with, so then the question I suppose is, suppose you have a set of linear equations, right? Or a matrix equation, which is homogeneous, and suppose it has two solutions. At least, suppose it has more than one solution. Then how many solutions does it have? If it has two solutions, right? You could add them together and get another solution, and then you could add that. You could add that to the first solution, and you could add. You could add again. You can carry on as much as you like. So as soon as you have two solutions, you have infinitely many solutions. In fact, as soon as you have just one non-zero solution, because you can multiply by any scalar, and the scalars are in R, so there's infinitely many scalars. As soon as you have a non-zero solution, you have infinitely many solutions. So this fact of S being a vector space means that for a homogeneous system of equations, for a homogeneous system of linear equations, there are either infinitely many solutions, because if you have a non-zero solution, then you have infinitely many solutions. and suppose you didn't have any non-zero solutions, right? You always have the zero solution, right? Because the system is AX equals 0, and if you put 0 there, if you put 0 for the x, it'll always work. So you always have the solution 0. So there's either infinitely many solutions or one solution, the zero solution. Those are the two options. So we said quite a lot then about what the solutions, or the set of solutions to this system looks like. This set, the set of solutions to the homogeneous system, it's a subspace, right? But it's such an important subspace that it has a particular name. This S is called the null space of A. So you can write it like that: the null space of A. All those x's that solve that system, right? So it's called the null space. There will be, each vector space will have many different null spaces, because what the null space depends upon the transformation in question. Suppose you had a different transformation, B, right? And that corresponds to having a different transformation, that corresponds to having a different matrix, which corresponds to having different coefficients in this system. So if you have a different system of linear equations, you have a different matrix in the matrix equation, and you'll have the null space of B will be something different. It'll be this. And maybe in this case example we looked at, the null space was that line, but maybe another null space will be that line, or maybe another null space will be the whole of R2, or maybe another null space will just be the point on the origin. Yeah? Mm-hmm. It's just another word, a fancy word for this set, which I've been calling S, the set of solutions to the equation AX equals 0. It's a subspace, but it's the subspace that is the set of solutions to the equation AX equals 0. So if I say null space of A, that means the subspace that is the set of solutions to the equation AX equals 0. So if you say null space, you must always say the null space of A or the null space of B, the null space of a particular matrix. Okay. Any more questions about this stuff so far? You want some time to write stuff down? Okay, so I'm going to try and carry on. Okay, so all of this stuff we're doing, all of this solving this homogeneous system of equations, that, if you remember from yesterday, was actually, that's a simplification of the real problem. The real problem was not to solve, which I posed initially, was not to try and solve or try and understand the solutions to AX equals 0. It was to try and understand the solutions to AX equals B, where B doesn't have to be 0, doesn't have to be the zero vector. So now we're going to move on to that problem. And hopefully, I mean, it turns out that the solution to the simpler problem is very useful, essential really, in understanding, in saying what the solution to the more complicated problem is. So remember, the more complicated problem was, well, it's called a non-homogeneous system of linear equations because it doesn't have, it's not homogeneous, it doesn't have zeros on the right-hand side. So, non-homogeneous. I looked it up. Non-homogeneous system of linear equations. Okay. And that's something like ax equals b. We actually started with this. We started at the beginning of last lecture with a system of equations, and we reduced it to this matrix equation, ax equals b. This equation that is about the linear transformation, again, from Rn to Rm, that is about the m by n matrix, and it's equivalent. It's a simpler way of writing this system. So it's non-homogeneous. So this b on the right, that doesn't have to be 0. And there's got to be m of these equations. Okay. So again, we want to look at the set of solutions to this. So we want to look at this set S, which equals all those x's in Rn such that ax equals b. The same questions. What is the structure of this set? How big is it? Does it have anything? Is it empty? Does it have anything in it? If it has stuff in it, how much stuff does it have in it? If you have one thing in the set of solutions, how do you get another thing in the set? How are the different elements of the set, the different solutions related to each other? So I think probably the first thing would be, maybe it's a vector space as well, right? Let's check. Let's see if it's a vector space. So to be a vector space, you have to check that see if it's closed under vector addition and closed under scalar multiplication, right? So let's try, what do you want to try? Scalar multiplication or vector addition? Addition. Okay, we'll try addition. Okay, so suppose we had x and y in the set. The question now is x plus y in the set? Is x plus y a solution? Okay, so x and y being in the set, that's the same thing as saying that ax equals b and ay equals b. X plus y being in the set, that's the same thing as saying a of x plus y equals b. Now, what can I do to this a of x plus y? So, I mean, the A is still a linear transformation, it's still a matrix, so it still preserves the addition, right? So you still have this becoming that, right? Okay. But what does this thing say about ax plus y? This thing says that if you take ax and you add, ax plus ay, and ay, what would you get? You'll get b plus b, right? But this other side, the one side says you'll get b plus b, and the other side says you'll get b. So the two sides are not equal to each other. So in other words, this is not true. X plus y is not a solution. It's not in that set. Is that okay? Did everyone follow that proof? Or that disproof? You could...
It's because like the sum gives us 2b.
Yeah.
Instead of b, that's why.
Yeah, exactly. The sum gives us 2b. So in the homogeneous case, it was fine that it gave us 2b because b was 0. And 2 times 0 is 0. So that's fine. But in this case, it's not fine because b is not necessarily 0, and b plus b is not equal to b. Okay. The scalar multiplication one would actually fail in a similar way. You'd end up with, on the left-hand side, you'd end up with alpha times b, and on the right-hand side, you'd end up, oh, on the left-hand side, you'd end up with, on one side, you'd end up with alpha times b, and the other side, you'd end up with b. Anyway. So it's not closed in a vector addition, so it's not a vector space. Okay. So that's why this is a harder problem than the case where the homogeneous case. So what structure does it have? I think one way to think about this is, let's see where we can use the homogeneous case. So let's say we have x, which is a solution to the non-homogeneous case. Oh, sorry, the non-homogeneous case. The non-homogeneous case. And also, let's suppose we have a z that is a solution to the homogeneous case. Can I combine these in any way to get another solution to the non-homogeneous case? So, yeah? Okay, let's try that. So, is x minus z a solution to the non-homogeneous case? Is a of x minus z equal to b? Okay? So what? So a of x minus z, what does that come to? So it's a linear transformation, so the first step is always to, well, you could actually rewrite this as a of x plus, and then the scalar is minus 1, and then z. But this is a linear transformation, so it preserves addition. So that's the same thing as a of x plus a of minus 1 z. But it's linear, so it preserves scalar multiplication, so it's the same thing as minus 1 times a of z. So that's the same thing as ax minus az. And what is ax? Ax equals b, because x is a solution to the non-homogeneous case, and az equals 0, because z is a solution to the homogeneous case, and b minus 0 is b. So x minus z is a solution. So it seems if you take a solution to the non-homogeneous case, and you subtract a solution to the homogeneous case, you get a new solution. So we found a way of getting new solutions from all solutions. In fact, you don't actually, to make things simpler, you don't actually have to subtract. You could actually add the z, right? If this was a plus, then all this would still work. So this minus 1b would be plus 1. It would be 1. You'd have b plus 0, which is 0. I mean, this is effectively, it's partly because if you have a solution to the homogeneous case, right? If you multiply that solution by minus 1, that'll still be a solution to the homogeneous case, because the solutions of the homogeneous case are closed under scalar multiplication, and minus 1 is a scalar. So she subtracted a vector from the homogeneous case. She subtracted a vector, but that's really the same thing as adding a vector from the homogeneous case, because if that vector is there in the set of solutions, if that vector is there in the null space of A, then so is minus of that vector. Okay, and I think I'm going to stop there for now. What I'd like you to try and think about for next week is, so we found that basically if you have a solution x to the homogeneous case, right? You can make a new solution by going x plus z, right? Can you get all the solutions that way? Or are there solutions which are not equal to solution from the non-homogeneous case plus solution from the homogeneous case? Actually, are there even solutions which are not equal to this particular x plus the z? So if I give you just one solution to the homogeneous case, but I give you all the solutions to the homogeneous case, can I then get, just by adding on the things, can I get every solution, or are there other solutions to the homogeneous case? So maybe think about that for next week. And then just for what remains, then I'd like to talk about what I said at the beginning about, like, how is this, how do people think this has gone? What can I change? Can improve, and that kind of thing. Does anyone have any comments or questions or anything like that, or suggestions? Yeah?
Maybe sometimes we need to examples, like give us a chance to try and figure it out for like 2 minutes by ourselves.
Okay. Anything else? So you should definitely, if you have like comments, questions about this game, or obviously maths questions, but you don't want to bring them up now, then you can please definitely email me, tnbewu@gmail.com, or come to my office, M316, and tell me about it. Because it's hard for me to know how I'm doing. I'm really worried. I'm worried people aren't following. So on the one hand, I'm worried I'm worried people aren't following, but on the other hand, I'm also worried that I'm asking you insultingly simple questions. But I don't want to say, hey guys, this is a really simple question, because then that's also like, well, maybe it's simple now to me after years of studying maths, but then it's not simple to you. So I want to know, are people following? Are the questions that I ask you too obvious? Or okay. Okay. Well, also maybe think about it over the weekend about how you want this class to be, or how you want things to change or be better. Yeah. Okay. You don't have to call me sir though, because that's also a thing I'm worried about, as reproducing bad hierarchies and power dynamics and things. That I don't like or support. So okay. So just call me Thomas. Okay, you can go now, or you can come and ask questions or what. But yeah. There aren't consultation times yet. They're only going to be set, I think, when timetables are settled. So I should be in my office generally from after the lecture until just before the tutorials, which start at 2. So I should be there generally at that time. If I'm not there, then just ask the people there if I'm coming back soon. And if you want me to be there at a specific time, then just email me and say, I want to come at this time. Okay.